100 nice simulations.
These are just.
All right.
Wait, why?
It might seem bizarre that you can actually build structures out with the reals that don't have these properties that are really nice. Real numbers and real analysis is usually a prerequisite for topology, but I think the students that took topology without real analysis fared better than the students who didn't, because the real analysis is just for the reals, and every example that you have will come back to that. It's almost like you can't change what you're seeing. This is called the completeness property of R. I need to erase this. This might seem so obvious. They gave you nice sets to look at that are like that you can draw and see, but every non-empty bounded subset of the reals has will have an upper bound and have a lower bound. That makes sense. You can actually visualize that, and therefore it's going to have a supremum and an infimum. You can't guarantee there's a max or a min, but you can guarantee that there's always going to be a super inf, and that's what allows you to do nonlinear programming. The feasible set, if the feasible set is bounded, you know that the maximum and minimum or the optimal values are going to either happen at the boundary or inside. All those theorems that you had in OR, they come from this fact that any bounded set has a sup and an inf. And you can ask yourself, where wouldn't that happen? Well, then take topology. That's where you see those weird things where it doesn't happen. But the reals has these nice properties, and that's why we like working with the real numbers. And that's why you started, I think, back in 6th grade, wherever you first saw irrational numbers and started working with real numbers, we fixate on it. We fixate on so much that we just only give complex numbers a little nod. We even avoid it in MA 103. It just drives me crazy. Because, you know, if you find the eigenvalues of a matrix, they're complex usually. If you make a random matrix, they usually are complex, the values that you get for the eigenvalues. But they avoid it in MA 103. And like, but then shouldn't talk about eigenvalues really, because the idea of eigenvalues is that matrices have a map that takes boxes of numbers to the complex plane, and then the complex plane we understand, so we work with the numbers. It's like you're reducing the entire box of numbers to complex numbers, kind of like an R squared for statistics. We're taking a line and a scatter plot of points and reducing it to just one number that tells you a lot about what that scatter plot looks like. So I can't stand that they avoid complex numbers in 103, but it'd probably be a bloodbath if they did. So I don't know. I don't know if that's a good idea. So when I showed you that the square root of 2 is irrational. We use square root of 2 since you first started learning about things like the unit circle. And you just think of square root of 2 as square root of 2, but it's really just a symbol. Square root of 2 is just somebody made up a symbol to represent square root of 2, because you can't actually write down square root of 2. You can say 1.1 or 1.41 yada yada yada, but that yada 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 is a big deal. It's like you can't actually write down the whole thing. And so it's not necessarily obvious that that number exists. And this is true. Isaac's the only one who's taken abstract algebra, but when you do a field extension, so you have something and you want to like extend your field with a new root in it, that's just a symbol. The imaginary number I, is just a symbol. It represents the solution to x squared plus 1 equals 0. So then you can start saying, like, if I have I squared plus 1 is equal to 0, then I know some things about I squared and I can actually do stuff with it. It's a symbol that represents something that you actually can't see. And so square root of 2 is actually just a symbol. How do we know though? So we can say, okay, all these numbers don't exist. Like, I know that something there is there. There's a gap. I don't have a solution to x squared is equal to 2. How do I know it actually exists at all? So I'm going to show that that square root symbol actually exists. So the first time I actually encountered this was I had a friend teach me abstract algebra. I never took it. And I was teaching it, and then he was trying to show me something, and he had put something like a solution to this is, he put a Greek symbol. And I asked him, what is that? And we're used to having solutions be numbers. Like, what is that? And he just wrote it down again with more darker chalk. And like, no, but what is that? So he was trying to tell me that that's just a symbol. I don't know what it actually is. It's just a symbol. And every time he tried to explain it to me, he just got louder and louder. But I just didn't understand him. Like that, we're so used to this idea that when we solve things, there's a numerical representation, and sometimes there's not. I is an example of where you don't have a numerical representation. We just know it exists in the complex plane. So that's where we're going. You did some of this stuff in abstract too.
Yeah.
What book did you guys use? Oh yeah, so that's a good book. I remember that Dr. W was going to use that. So I know the soup exists, so I'm going to use the supremum. Actually, it should be in. No, it's the soup. So if this is bounded above, I know it's got a soup by the completeness property of the real not line. And so I know that the soup of that set exists. I now need to show that that soup is actually the solution to x squared equals 2. Mulling this over, Alex?
What?
Mulling this over? So you guys just worked with this set. You had rationals, right? You just like, so you can actually visualize the stat. It's capped above by square root of 2. I think you guys had it capped below by square root of 2. I could have gone the other way. So you can kind of visualize what this is. So you have a bunch of things in the set and it's capped above by this hypothetical square root of 2, which we don't know exists yet. So to be a soup, you have to have two things. You have to have that it's non-empty. Is this set non-empty? Can you think of something where you square it and it's less than 2? Give me just one thing that's in there. One. So the completeness property says that it has to be a non-empty set. And the second property is it has to be bounded above. I just have to find one bound that's kind of nice to show it's bounded above, like has an upper bound. So can you think of something that will squash that set? Just one nice number. Doesn't have to be a that'll squash that set above. So if you graphed it, 2 squared is 4, so that'll do it. So that set is bounded above by, I don't think it'll be bounded above by 2. I think you need take something like 4, right? That'll work. This does this. You can do 100 if you want. That'll work. Because 2 squared, yeah, so 2 will work.
Why would 2 work? I thought 2 squared is. Wouldn't 2 squared be greater than 2?
Yes, and you want it to be greater than the elements in that set.
Oh, this not this.
Yeah. So you know you can use your intuition to say it's 1.14 blah 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 whatever it is. 2 is bigger than that, right? So 2 certainly covers it. But I don't even add. So I got a guess here. Is anybody taking nonlinear programming right now? Where you're just finding optimum values. I mean, I'm simplifying it, but you're finding optimum values for nonlinear functions over a feasible set. It's the same thing. You're looking for, you use this theorem to say that it exists. Next step is to assume, on the contrary, x squared is strictly less than 2. We're going to show that can't happen. So here's the strategy. You're going to show this can't happen, and you're also going to show x squared can't be bigger than 2 either. Strictly bigger than 2. If it can't be smaller than 2, and it can't be bigger than 2, it's got to be equal to 2. This only, because we know the soup exists. So it's got to be one of those numbers. So if it's not in the number line below 2 and it's not in the number line above 2, it's got to be exactly 2. Make sense? So this is a picture I was waving around my hands. So you're gonna show that this possibility can't happen. It can't be in that range by contradiction. You're gonna show the same thing over on this side. It can't happen. Well, the only other possibility left then, if it exists, is the only other real number left is 2.
Matt, what is the backwards V thing again?
There exists. The strategy is to actually add just a little bit more to this X and then show that it's not gonna work. X can't be an upper bound because of this. Yeah, X is defined to be the supremum. So here's how you do it. It's actually high school algebra. Or as one of my profs used to say, high school commutative algebra. Believe this? If I have any natural number, if I square it, 1 over n squared is going to be bigger than 1 over n. Take n equals 2. 1/4 is going to be smaller than 1/2. So when you square this thing, for any n, that's going to be true. So then, x plus 1 over n, like this. Good old high school algebra. You get this. And then I'm just going to replace that bound of 1 over n squared above by 1 over n. Stay with me, Cooper. The 1 over n squared. So we do this a lot in our analysis. This 1 over n squared is going to be smaller than this. All right, I'm going to leave you guys off with this. I hate to like drop you in the middle of it, but this is pretty long, but I'll go through this again when we have class on Monday so that you can see like the whole thing back, and then I'll give you one more problem to do with this. Yes.
I just got like.
It's
like. All right, hey, I'll be.
Yeah.
But that's where it's. No, it's right next to it.
You-
Really awesome. Line out here. I don't think I'm taking.
Yes. No, I
Like, we'll leave it out.